So welcome back. In this short video, I'm going to briefly review the properties of amplitude and period from the last video, and then give you an example question to practice with. So we understood that when you have an oscillator, that two very important properties of the oscillation are the amplitude of the oscillation and the period of the oscillation, or how long it takes between cycles of the oscillation. And we understood that the amplitude of the oscillation is determined by how you set up the oscillation initially. So you could either displace your oscillator some amount away from the equilibrium position, and then the more you displace it, the larger the amplitude of the oscillation will be. Or in another example, you could give the oscillator some velocity when it's at the equilibrium position. For example, you could have a collision, you could hit it with a hammer, so it has some initial velocity, and then it starts oscillating. And then again, how hard you hit it depends, will determine how big the amplitude is. What about period? So one thing we demonstrated last time was that the period of an oscillator doesn't depend on how much you displace it originally or how much initial velocity you give it. For all sorts of different amplitudes, you get the same period, as long as we're talking about an oscillator where the restoring force is obeying Hooke's law. And remember, that's something that is almost universally true if we are just talking about small oscillations around an equilibrium position. So that's really important, that the period is a basic property of your setup. And so a system like the one here is going to have a natural frequency that it wants to oscillate with. What does that natural frequency depend on? What sorts of physical properties of the system? Well, generally speaking, it depends on the mass of the object that's oscillating. And so if you have a larger mass, then it's going to go slower. Or if you have a smaller mass, then it'll oscillate faster and you'll get a higher frequency. And this is basically just because the forces, the same force acting on a smaller mass will produce a larger rate of change of velocity. And so that oscillation is going to happen faster. The other thing that this oscillation frequency will depend on is the strength of the restoring force. So if I displace it a certain amount, how strong is that force pulling me back? In terms of Hooke's law, that is determined by the constant K that appears. This is the what we'd call the constant of proportionality between the force and the displacement. So in practice, what it means is that if I have a stiffer spring, then I get a higher frequency oscillation because it's a larger restoring force. And so I mentioned last time that this mass on a spring is actually a good model for a lot of oscillators that we have in musical instruments. And so I wanted you to just try to apply the intuition that we've just understood to this example where it's talking about a few different guitar strings stretched between the same length, and also the guitar strings are all the same thickness. But one of them's nylon and the other two are steel, and one of them has one of the steel ones has a lower tension than the other two. So I want you to try to rank the vibration frequencies of these three guitar strings shown. So pause the video, take a moment to try that, and then we are going to talk about it. All right, so in these ranking questions, what I generally like to do is just try to start with two of the things that only differ in one property and then compare those. And then we could compare another thing to one of the first two. So I'm going to start by looking at the first two here. And so what we have is the information that the tension in these two strings is the same. And the tension is something which kind of determines how much if we displace the string, that's going to determine how much force is going to pull it back. So if I had no tension, that means the string is just sitting there floppy and it wouldn't have any restoring force at all. So the tension, which is the thing that I change by turning the tuning knobs on a guitar, so I make it I increase the tension or decrease the tension. That's the same in these two cases. Okay, so that is basically that the restoring force is the same. The difference here is the material. 0.5 millimeter thick steel is going to be heavier than 0.5 millimeter thick nylon, which is kind of like plastic. And so we have the same restoring force for these two strings, but we have a smaller mass for the nylon. And so what we're going to expect is that nylon will end up changing its velocity quicker with a certain amount of displacement, and so the oscillation is going to be faster. So we expect a higher frequency oscillation for number 2 as compared with number 1. Okay, so that narrows it down to one of the last 3 options. And now let's compare number 1 with number 3. Okay, because those are the same material, and the only difference is the tension, which is lower in the case of number 3. So it's the same mass, but a lower tension. So that's like a smaller force acting on that to bring it back to equilibrium. And so what we would expect then is that in number 3, that string is going to take its time a little bit more to move back to the equilibrium position. We expect a slower oscillation and so a lower frequency. So we expect that we said that 2 was greater than 1, but we also now have understood that 1 should be a greater frequency than 3. And so the correct answer here is that 2 is greater than 1 is greater than 3. And so just to finish, well, you might be wondering, in a real guitar, what is it that determines the fact that you have different frequencies for different notes? And I have my guitar here, so I just wanted to show you quickly. Let's just zoom in here on this. So if you look at the strings, then this is a steel string guitar, but you notice that the strings on this side are much smaller than the strings on this side. So the mass for the strings playing the low notes is much larger than the mass for the strings playing the high notes. And it turns out that the tensions of all of these strings, they're different, but they're not too different. And so most of the reason why the notes on the guitar sound different from each other, that some are higher, some are lower, most of the reason is just because some of the strings are lighter and other ones are heavier. And so the lighter ones, as we learned, are going to play a higher frequency because the same amount of force pulling on them will cause a greater rate of change of velocity, and so that will lead to a faster oscillation.